of class. Okay, so left this table up from last time. We kind of mentioned momentum is the one thing in linear motion we haven't talked about a rotational equivalent of. So we're going to do that now. We're going to talk about angular momentum. And we're going to start, say we have Newton's second law for rotations. We have torque is equal to I alpha. And for now, we're going to consider just like a rigid object. And remember, alpha is the change in angular velocity over time. Now, we've done this a few times where, say delta AB, where say A is constant and B is a variable. That's A times delta B. I've shown that a few times. Well, we can go backwards as well. We can go this way. It's an equal sign, works going either way. So what we can do is we can move this I into the delta. So we can say that this is delta I omega over delta t. And we're going to define this quantity I omega to be angular momentum. So just like momentum is mass times velocity, replace mass with moment of inertia and velocity with angular velocity. And just continue what we've been doing by making these substitutions. And remember the different version of Newton's second law, the one Newton himself used. Force is equal to the rate of change of momentum with time. Again, if we replace force with torque and momentum with angular momentum, we get this equation. Torque equals delta L over delta T. So, momentum and angular momentum, we have that same relationship between the translational and rotational variables. Okay, now we had to assume that this step here only works if I is a constant, but we define angular momentum this way regardless. And Newton's law in general is valid. But, so this is that other form of Newton's second law for rotations. The other is torque equals I alpha. Anyways, so this is how we define angular momentum. Let's talk about units. Remember, I is kilograms times meters squared, and then omega is radians per second. We leave out the radians. Kilogram meters squared per second. That's kind of how we have to leave it. You'd think they'd give this a name, like we do for some other things. But no, as far as I know, there's no name for this. So, like a Newton is a kilogram meter per second squared. You just give it a name. But no, it hasn't been done as far as I know. I guess we could play around with a little bit, though. It doesn't do much good, but let's see. We could write it like this. Kilogram meters squared per second. And let's multiply and divide by a second. A kilogram meter per second squared is a Newton. So this would be equal to a Newton times a meter times a second. Still three things, just one of them isn't squared, so usually I just leave it like this. Okay, so angular momentum defined as a moment of inertia times angular velocity. And this is a very useful form for Newton's second law. And I'm going to write it this way, because angular momentum is a vector and it does have a direction. Okay, now the direction is in the same direction. We can write that as a vector equation as well. So remember, angular velocity has a direction given by the right-hand rule, and that's the same direction as the angular momentum vector. Now, very often, again, fixed axis of rotation, we can say that we can use either plus or minus or clockwise or counterclockwise to describe it. But there's a very interesting example where the axis of rotation is not fixed. And we can actually show one of these in class. It's a pretty cool demonstration. So maybe during a lab, I'll see if I can fit that in there. But we're going to kind of follow what we did when we were talking about linear momentum. Let's say we have a system where the net torque is 0. So we could write this as the net torque. So if the net torque is equal to 0, that means that the change in angular momentum is 0. This is called conservation of angular momentum. And there's a very classic demonstration that, Isaac Newton probably didn't write this, but every other physics book ever talks about this. And that is the, look at like an ice skater. I don't know, I never watched this myself, but I hear that, there's a thing they do where an ice skater spins around and they can speed up or slow down. And, with ice skates, friction is pretty insignificant, at least over short time periods. So let's say you're ice skating and you start spinning around. There's, friction would exert a torque, but if we can neglect that, your angular momentum is constant. And angular momentum, just in magnitude, that's I omega, that has to remain constant. Where omega is how fast you're spinning. That's your angular velocity. And how can you speed up or slow down? You can do that by changing your moment of inertia. So there's a cool demonstration. I'll try to do this one day when we're in class, where there's a rotating platform you can stand on, and you can hold these masses in your hands. And again, we'll do this in class, but you stand on this platform and hold these masses out as far as you can. And remember, moment of inertia it depends on how much mass there is, but r is the distance that the mass is from the axis of rotation. So if you're holding these, well, they're not that heavy, they're only a few pounds, but if you're holding them outwards, they're very far away from your axis of rotation, and so you have a pretty high moment of inertia. But then if you pull your arms in, your moment of inertia decreases. And so because L is constant, if you decrease one variable, you have to increase the other. And yes, spinning skaters can do this as well. They don't really have masses that they carry around with them when they're skating. That just makes the effect more dramatic. But if you just if you're standing like this and you pull yourself in, you'll speed up. And then if you kind of extend yourself, you'll slow down a lot. And it's pretty cool to actually do this one in class on that rotating platform. But I don't think we'll have a class or do a lab about this until after the exam. But anyways, that's one kind of interesting example of angular momentum. Now, I mentioned in the very beginning of class when we were talking about units. And, time has to be defined in a certain way. And the original clock was just the Earth, because the Earth rotates. And so, it's periodic. We can define a day to be the time it takes to complete one rotation. But don't mention that clocks are not perfectly accurate. Like the Earth is not a perfectly accurate clock. The length of the day is not perfectly consistent. So I'd say here's the Earth. So here's the equator. And here's our axis of rotation. If you've ever seen a globe, they're always, tilted to the side. It's like about a 23-degree angle. And the reason is that the Earth's orbit defines a plane, and our axis of rotation is tilted with respect to that plane. That's why they're always drawn that way, but we're rotating about this axis here. And that's just like the spinning skater. So our angular momentum is basically constant. However, our moment of inertia is not, because there are things moving around on Earth. Mainly things like air currents or ocean currents. If you picture a mass of water, say, moving, like north, this would be a small effect, because it's not like there's a net movement of water north, but it can affect densities, different, like salt content or something. But picture like you have some mass move upwards. Then it's going to be orbiting at a smaller radius. Like if you look at the North Pole, say here's the equator. If you take some mass from the equator and move it upwards, its radius will be smaller. And so that's like bringing mass inwards. The Earth's rotation would speed up a little bit as a consequence. And volcanic eruptions, they move matter outwards to higher altitudes, like all the dust and particles get shot up into the atmosphere, so they're at a farther radius that would increase the moment of inertia, which would slow down the rotation of the Earth. And then those particles eventually come back to Earth, and then it speeds up again. But there's actually a picture I've seen that shows very small changes in the length of a day. And it's just due to things moving around. Plate tectonics, continents are moving around. They do so very slowly, but all these things, the Earth is an active place, and so the length of the day, our moment of inertia is not perfectly fixed, and also you could argue our angular momentum doesn't have to be perfectly constant either, because there's torques acting on the Earth, things passing by. So that could have small effects as well. Okay. What if something, let's look at an example though where there is a net torque. And this is an example where we have to take the angular momentum vector in three-dimensional space. But say we have a spinning top. So say we have it vertically and we give it some rotation. So say it looks something like this. And you balance it, and say you set it down. What's going to happen? Obviously, it's going to fall over. I think if you perfectly balance it, it'll, it's possible to keep it straight up. But if it's balancing on the tip, any slight nudge, it's falling over. But what if you spin it first? Does it fall over? Now, if you've ever seen a spinning top, no, what it does is, say this is the axis, it starts to fall over, but then it does something strange. It does this. This axis starts going in circles. So why does it do that? Let's say it starts to fall over because it's not perfectly balanced. So I'll just rotate this a little bit. I'm just redrawing it. So it falls over a little bit. So let's say this is a profile of our spinning top. And let's say the angular momentum vector is in that direction. So it's along the axis of rotation. And I drew it like it's spinning this way, right-hand rule, thumb points that way. And what forces are acting on this top? I'm kind of regretting drawing the vector here. Let's say the center of mass is here. So this is the center of mass. We have gravity acting downwards. And a normal force. And that's it. Now let's say that the point of contact with the ground is our axis of rotation. The torque due to the normal force is 0. Because that's where, that's the force is applied at the axis of rotation. But the torque due to gravity would be mg times the lever arm. That's not 0. And so there is a net torque acting on this spinning top. What direction is this torque? Well, we use the right-hand rule. If the top is in this orientation, like if it's here, gravity is going to cause it to topple this way. And so you curl your fingers in that direction, torque would be into the board. And so it's going to cause the angular momentum vector to rotate into the board. So it's going to go this way. So if this is our spinning top, it falls over a little bit, but then it starts rotating in this direction. And if we spun it in the opposite way, same thing would happen. It would just spin in the opposite direction. And that's called precession. And again, this is one of those topics where it really helps to be actually in a classroom to do demonstrations. There's a lot we can do with rotations. Very interesting and not always intuitive behavior for rotations. But precession is very important. And again, it's just that spinning top. It falls over and then the axis of rotation forms. It just spins around. Now, the Earth is basically kind of like a spinning top as well. So let's draw the Earth again. And again, here's our axis of rotation. Should go through the center and draw it perfectly. But if you go outside at night and just stare up at the sky, if you watch it long enough, obviously, like if you could watch it, maybe if you go up to the North Pole in the winter when the sun never rises, if you look at stars, you could follow them if it was clear out over the course of an entire, day or night or whatever. And you'd see that stars move in circles. And the closer they are to, like, we call this the North Celestial Pole. So if you looked at a star, and there's also a celestial equator, which would be, there's a celestial sphere. Because if you look at the sky, you can't really tell distances. So you can imagine the celestial sphere surrounding the Earth. And you have a North Pole and you have an equator. If you look at a star on the equator, it's going to make a very big circle around the North Pole. But then, depending on where the star is on the sky, so again, if you look up, say here's the sky, stars are going to do this. They're going to form these loops around the center. But there's one star right in this middle that doesn't really move, at least not a very noticeable amount. And that star, because it's at the North Celestial Pole, it is called Polaris. And we're very lucky how this worked out. Because it's also called the North Star. And, all the other stars kind of circle around the sky except for Polaris. And that's because Polaris happens to be directly above the North Pole. Or very close to it. It's about maybe 1 degree off. But, close enough. It's actually more accurate than a compass is, because a compass doesn't point to the geographic North Pole, points to the magnetic North Pole, which is different. And overall, looking at Polaris is more accurate than using a compass for determining north. But we're very fortunate to have that because the Earth is acting like a spinning top as well. There are torques acting on the Earth due to the moon that cause it to precess just like that spinning top. The only difference, if you have a top and the axis might do something like this, it might take a second to complete a circle. For the Earth, the period of precession is about 26,000 years. So you picture, here's the Earth's axis of rotation. It's doing this as well. Right now it happens to be pointing at a star, which is called Polaris, which fortunately is a big enough star that we can see. But over time, we're going to move away, and Polaris is going to get farther and farther away from the North Pole, and eventually we won't have one anymore. Now, at this point, we don't really need it. We have much better ways of navigating, like GPS. But historically, that was a very important navigation aid. And again, we don't always have this. It's just fortunate that our modern civilization, it's pretty much always existed. And it will for several thousand more years. I don't know if they still print star atlases, because now everything's on the internet, but star atlases, traditionally they update those every 50 years, and one of the big reasons is because the Earth is precessing. The axis is rotating. Another reason, though, is stars actually do move, because everything in our galaxy is moving. So they have to periodically update those. But interestingly, Polaris will one day no longer be a good navigation aid. We just lucked out on that one. All right. I think we have one more thing to talk about, and that'll be it for this section, Chapter 9. So, that'll be it before the exam. And we're going to go back and look at orbits. So we know with circular orbits, but more realistically, orbits are elliptical. This is a massive exaggeration of an ellipse or an orbit, at least for planets. There could be objects in the solar system that orbit like this. But say this is the sun, and say this is, maybe it's a comet or something. Planetary orbits are much more circular. Now, we can consider a comet to be a point particle. A point particle is where the dimensions of the objects are much smaller than the distance between them, and that would definitely apply to objects in the solar system. So say we have a comet with a mass m and a radius r. That could be any object in general. And it's moving with a velocity v. So this object has angular momentum equal to I omega. Now remember, I for a point particle is mr squared. And we can write that as mr times r omega, where r omega is just the tangential velocity. So we have angular momentum is mrv. So the angular momentum of a planet, and we're treating it just as a point particle. And there's a force of gravity acting on this planet. However, the force of gravity, the torque acting on this object is zero. Why is it zero? Because the force of gravity is directly towards the sun. And so the line of force passes right through the sun. The lever arm is zero. And so the net torque on the planet is zero, which means that the angular momentum is conserved. Or L is a constant. And we can divide by m and just say L over m is a constant. Which means this product R times V is constant. And so what that means, we have an elliptical orbit. There's kind of two special points. They're called perigee and apogee. I'll just call them like P and A. Perigee and apogee. Not sure if I'm pronouncing those right. But that's the closest point, and apogee is the far point. And we can see that they have to be moving at very different velocities, or depending on how elliptical the orbit is. Because at apogee, R is larger, and so remember, we're multiplying two things and getting a constant. So if we have a large radius, we have to have a small velocity, which means it's moving slow when it's farther away from the sun. And if R is smaller here, it would have to have a larger velocity. And so we can see that the velocity of this, this object is constantly changing as it's moving around its orbit. This product of the radius times the velocity is constant. And so yeah, as the radius is changing, the velocity is as well. And we can even talk a little bit more about how it's changing. Let me just erase that. And let's consider some time interval. Now, let's assume that this is a small time interval. I'm greatly exaggerating the size of this picture, just for clarity. But I'm going to like the area of this wedge here. And we can kind of approximate this as a triangle. And so the area, let's call that delta A, would be the area of this, it's the area of this, I'm not sure what geometric shape that is, but that arc here. But we're approximating that as a triangle, and as this angle gets smaller, then the difference between this triangle and that wedge that it carves out, that gets smaller as well. So if we go, as long as we make the angle small, we're fine. And from our arc length formula, this is r times theta. So we'd have 1/2 times a base, which is r, times a height, which is r times theta. And so we have 1/2 r squared theta. That'd be delta A, the area of that wedge. And what I'm going to do is, let's see, if we divide by delta t, now theta over t, the delta to be the time interval from here to here, if we divide by that, we'd have 1/2 r squared omega. And just remember angular momentum of this object, that's mr squared omega. Remember, L is I omega. I in this case is mr squared. So r squared omega is L over m. So we can say that delta A over delta t is 1/2 times L over m, or L over 2m. And remember, this is a constant, because the angular momentum is constant. And so what we found is that this delta A over delta t is constant, where this is one of Kepler's laws, this equal areas in equal times. So if you look at 2 points on the orbit, I'm going to erase this line, kind of use that to derive it. But if we go like some time interval here, if there, time it takes to do this, it's going to sweep out an area equal to this wedge. And again, if you consider a different time interval, or the same time interval just at a different place, let's say we start here and go through delta t, we have to go through the same area. So if those time intervals are equal, these areas that are swept out have to be equal as well. And so we'd have to go through a much larger angle here because we're closer. It would have to be like a wider wedge here. And again, this is one of Kepler's laws. It's called like the equal areas in equal times. Now, we don't really use this equation. It's more like it's important because it's one of Kepler's laws. So, understanding Kepler's laws, but we don't really work with it numerically. Just the idea that we're going faster when we're closest to the source of gravity and slower when we're farther away. And so, Newton was able to prove Kepler's laws of planetary motion. Kepler actually had another law which is wrong, so he didn't prove that one. But otherwise, he was able to derive Kepler's laws, and that was one of those. Okay, so that'll be it then. And that's it for this section. So chapters 7, 8, and 9. And then just 3 more chapters to go.